Hello. In this podcast, we're going to learn about the quantitative analysis of energy flows. First, we're going to take a look at the mechanical energy equations. Then we're going to learn how to calculate changes in the storage mechanisms. And finally, we're going to learn a little bit more about work and power from a quantitative point of view. Let's get started. Let's review the energy equations involved, and we're going to focus just on mechanical energy. First, there's the conservation of energy equation, and that's the energy transferred in to the system or out of the system by work, less the energy dissipated by friction, is equal to the energy change in the object, specifically the energy change in the kinetic storage mechanism, the elastic potential storage mechanism, and the gravitational potential storage mechanism. And then when it comes to calculating the amount of kinetic energy, or the amount of energy stored in the kinetic mechanism, it's 1/2 times the mass of the object times the velocity squared. Or, since our conservation of energy equation focuses on the change in kinetic energy, the change in the kinetic energy is equal to 1/2 the mass times, in parentheses, the final velocity squared minus the initial velocity squared. When it comes to the energy stored in the elastic potential energy mechanism, the amount of energy is equal to 1/2 the spring constant times x squared, or in its delta form, it's 1/2 the spring constant times, in parentheses, the final position squared minus the initial position squared. Let's take a look at the final equation, which is the equation for the energy stored in the gravitational potential mechanism. And it is equal to the mass of the object times g times height. G is equal to 9.8 meters per second squared, and that is the acceleration due to gravity. In its delta form, the change in energy stored in the gravitational potential mechanism is 1/2 times the mass of the object times g times the change in height. Let's go ahead and take a look at some applications, how we use this. But first, let's look at our analytical strategy. First, as always, we want to identify the system. Second, we want to identify the storage mechanisms that are changing. And we want to determine if any energy is transferred into or out of the system. These three steps are things that we've already learned to do as part of our qualitative analysis of energy. Now, quantitatively, once we determine the storage mechanisms that are changing, we want to use the appropriate equations to calculate the energy flowing into or out of the storage mechanism. And then lastly, we want to use the conservation of energy equation to calculate the energy transferred into or out of the system. Let's take a look at our first problem. A 10-kilogram box is resting at the top of the ramp, and it slides to the bottom of the ramp. If we ignore friction, what is the box's speed at the bottom of the ramp? First, let's identify the system, and it's the box, the ramp, and the earth. Next, we know that energy flows out of the gravitational potential mechanism because it's losing height, and we know that it's flowing into the kinetic energy mechanism because the object is going from rest to moving. And there's no energy flowing into or out of the system. So if we look at our energy equation for the change in gravitational potential energy, we go ahead and plug in the mass, the acceleration due to gravity, and the change in height. Notice, as with any change or delta function, it's the final position minus the initial position. And in this case, that creates a negative number. And we can see that the energy change in the gravitational potential mechanism is 196 joules, and the negative sign means that the energy is flowing out of that storage mechanism. And finally, let's look at the conservation of energy equation. So the amount of energy transferred into the system is the work less any energy dissipated by friction, and that's equal to the change in the object's energy stored in these three mechanisms. Now we know, because there was no energy transferred into or out of the system, and because we could ignore friction, we know the left-hand side of the equation is 0 joules. And then we see that the change in kinetic energy, which we don't know, so we list the variable, plus 0, because there's no stretch or compression of the object to store elastic potential mechanism, plus the negative 196 joules, because that's our change in gravitational potential energy. And that leaves us with the change in kinetic energy is equal to 196 joules. Now the last step we need to do is find how fast the box is moving when it has 196 joules of kinetic energy. So we use our equation for the change in kinetic energy, and we go ahead and rearrange it to solve for the final velocity. And then we plug in our values for kinetic energy and mass, and we find out that at the bottom of the ramp, the box is moving at 6.26 meters per second. Let's take a look at another problem. Here, energy is transferred into the system. The box is at rest at the bottom of the ramp, and it's the same 10 kilogram box, and then you are pushing it to the top of the ramp where it also comes to rest. And notice that the height of that ramp is 5 meters. So ignoring friction, how much energy did you transfer into the system by the work transfer mechanism? Well, first, identify the system, and it is the box, the ramp, and the earth. Second, energy flows into the gravitational potential mechanism because the box increased its height. However, there is no net change in the amount of energy stored in the kinetic mechanism because the box is initially at rest, and at the top of the ramp it is also at rest. We know that energy flows into the system because you're pushing the box and you're not part of the system. Now we go to the quantitative equations, and we can calculate the change in gravitational potential energy. And we use our equation and come up with 490 joules. It's in the positive direction because that means that there's an increase in the gravitational potential energy. Finally, we can look at our conservation of energy equation, and we see that the work less the energy dissipated by friction is equal to the change in the object's energy stored in these three mechanisms: kinetic, elastic, and gravitational. Well, we know that there's no friction, so there's zero energy in the dissipated mechanism. There is no change in the kinetic or elastic storage mechanisms. And of course, we had 490 joule increase in the amount of energy stored in the gravitational mechanism. And so that means that the amount of work the amount of energy you transferred into the system by work is 490 joules. Let's look at one more example. Here we have the same ramp, but we have the box resting on a compressed spring, and this box is lighter. This box is only 1 kilogram instead of 10 kilograms, and the compressed spring is going to launch the box up the ramp, and when it reaches the top of the ramp, which is 2 meters off the ground, this box is still going to be moving with a velocity of 2 meters per second. So the question is, how much energy was dissipated by the friction? And we can see that the spring constant here is 400 newtons per meter. We'll need that information. Well, first, the system is the box, the spring, the ramp, and the earth. Energy flows out of the elastic potential mechanism because the spring goes from compressed to its normal equilibrium position, and there's energy flowing into the gravitational potential energy mechanism, the kinetic energy mechanism, and the dissipated energy mechanism. So there's the increase in the gravitational mechanism because the box is going higher off the ground. There's an increase in the kinetic mechanism because the box went from rest to moving, and there's an increase in the dissipated energy because we have friction. There are no energy flows into or out of the system, so nothing's being transferred. And we can look at our conservation of energy equation. I've kind of combined everything here. And so the work put into the system less the change in dissipated energy is equal to the change in the object's energy stored in the kinetic, elastic, and gravitational mechanisms. So now I went ahead and plugged in the information. We know that there was no energy transferred into or out of the system, so the amount of work done is 0. We know there's going to be dissipated energy. In fact, that's what we're being asked to find. And now I plugged in the numbers to calculate the change in the kinetic energy, followed by plugging in the numbers to calculate the change in elastic potential energy. Notice I put a minus sign in place of the plus sign because we had energy flowing out of that storage mechanism. And when energy flows out of a storage mechanism, it's a negative number. And lastly, I entered the numbers to calculate the change in the gravitational potential mechanism. So when we do the math, we find out that negative change in dissipated energy is equal to negative 28.4 joules. And so those two negative signs cancel each other out, and the amount of energy dissipated by friction as the box went up the ramp was 28.4 joules. So far, we've been calculating work by finding the changes in the different storage mechanisms. Now let's look at an equation for calculating work directly without having to find the changes in the individual storage mechanisms. Work is equal to the displacement an object is moved parallel to a force. So our work equation is equal to force times the displacement. Now let's take a look at power. Power is the rate at which energy is transferred. So it has SI units of joules, which is the unit for energy, joules per second, which makes it a rate. We know that joules can be written as Newton meters, so another way to express power is Newton meters per second. And in base units, it's kilograms times meters squared per second cubed. Of course, all of this is a mouthful to say and lengthy to write, so they gave it a special unit, watt, in name of a scientist, and the abbreviation for that is capital W. Most often we use either watt or joule per second. So let's take a look at the equation for calculating power. In its base form, it's the change in energy divided by the change in time. Since we're working with energy transfer through work, it's work divided by the elapsed time. And we can take that a little further. We know that work is force times displacement. So power is force times displacement divided by elapsed time. Now we can go ahead and just rearrange this differently. And notice that delta x over delta t is the equation for velocity. So another useful form for calculating power is force times the velocity that the object is moving with. So a couple ways here, or three ways to calculate power. It's the change in energy divided by the elapsed time. It's the amount of work done divided by the elapsed time, or it's the force times the velocity. Let's take a look at how we use these equations. You're pushing a box against a 30 Newton friction force for 10 meters, and you do that in 20 seconds. How much work did you do? Well, we're going to go ahead and use our work equation, and since we were given the force and the displacement, we're just going to use this version of work, and it's 30 newtons times 10 meters is equal to 300 joules of work that you did. What was your power output during this time? Well, we know the work from this first calculation, and we have the time in the problem. And so we're going to use this version of the power equation, which is the amount of work divided by the elapsed time, and it gives us 1.5 watts. This wraps up what we wanted to learn on the quantitative analysis of storage mechanisms, work, and power. I hope you found this podcast helpful, and have a good day.